I'm in North Carolina, I go, and it's amazing what people don't know, which I would expect them to know. But there has been a thought leader in this area for a number of years. His name is Jeremy Frey. We're humbled to have him present and give kind of the closing talk on this. I've known him for a number of years. He's had a significant influence on my thinking, and he's definitely been pivotal in highlighting the benefits of AI that we could get. So I'm going to hand over to Jeremy and let him give us his thoughts.
Thank you, Tony. Much appreciated the comments. Influencing you that's a definite tick on a career. You've done well out of it. So, so thank you all, and I want to thank everybody for their contributions. I had a little time listening to their videos and listening into the conversations based in the Netherlands and seeing some of the results coming from Malaysia. So let me share my screen and let's see if we can make this all work, and hopefully I can get this working. Okay, is that all okay? Hopefully you can all see that. Okay, so
yes, we see it. We see it.
Tony landed me with a number of things to explain and justify. I do describe myself these days as a physical and digital chemist. So importantly, for some things, I'm not an organic chemist, although I work closely with them in that they put molecules together, and I spent quite a lot of my career destroying them. So some of the stuff that I will say here comes generally from the work that we've done from the UK Science Programme, looking at chemistry and data, and some from my experience as a researcher in the physical chemistry areas. And others generally from interacting with a lot of people. That's been a great pleasure by working in this general sort of e-science area and now moving into this sort of AI machine learning. So I was tasked with my task is to kind of summarize what's been going on in the various discussions. And I've been adjusting slides a little bit as I've been going along and making some notes. And particularly to try and come down as to how we're going to shape the future. What are the critical issues? At least the critical issues as far as UPAC is concerned is this is the UPAC World Chemistry Leadership Meeting. We've got a lot to think about and a lot to do. And let me talk about some of these things. So one of the important things here is that UPAC is about pure and applied chemistry. And we want to look at the way forward in these things. Now, I think it's particularly interesting that it's pure and applied. As you will have heard from our speakers who covered a significant range from academic environments to industrial environments, and that's been true of the speakers in the other forum and generally in the Congress. What is really interesting here is that while in some ways the relevance of UPAC has been lost to some parts of industry, I think now with the rise of AI and machine learning, and by the way, I rather prefer the term augmented intelligence rather than artificial intelligence, that the relevance is coming clearer again. And in many ways, much of industry is ahead of academia. Perhaps the DeepMind example is one of the strongest to the community, but where we should be asking the question more than what has DeepMind done, which is significant. Maybe it's not solving all of the problems here with AlphaFold, but it's solving a lot. It's how were they able to achieve that? And academic groups less so, although because of the way it was then published, academic groups have certainly been able to use this and move on. I think there are some interesting lessons there. So what should UPAC be doing now? Well, some of this is certainly the digital UPAC theme that was part of the General Assembly. Bonnie has mentioned Leah's major contribution in having several themes running through here. Javier in his introductory talk mentions the color books that have a lot of information about UPAC's core area on nomenclature and terminology, and how the digital UPAC is looking at making those much more available and much more useful in a digital native environment. But also come to deal with the fact that, as Bonnie mentioned, data is at the heart of UPAC's existence, and ability to exchange that data and, as she put it, to create the language for chemistry, the international language for chemistry, is extremely important. So I don't think it should be a really surprise to anybody that I see, and I think we all see, a huge future, extremely busy future, and one that we need to attend to immediately for UPAC to be relevant for the machine learning AI era. Now, in general, I've thought for quite some time that what we're doing is some science, chemistry, but actually it's not just chemistry, it's biochemistry, it's molecular biology, it's materials. Nanotechnology is, of course, just supramolecular chemistry. A lot of this is chemistry, but we cross all the boundaries. So science is what we're investigating and working on. And the digital technoscape is how we choose to investigate it. And that's become much more significant in the last few years. To even more chemists. So computational chemistry has been on the rise for many, many years, has become routine by many synthetic chemists, but actually looking at the machine learning side and the AI side, I think has widened the scope here and shows everybody what the impact of digital is. On the other hand, I can, well, until recently, I could in principle order a ticket to fly to Sydney. I can't go there now, but could go there and book my ticket for the Opera House and even know what the sight line was and everything. And when you think of that compared to what we do routinely in the lab, what's the consumer side of the digital economy compared to the digital side of the chemical economy, I think you see we've got a lot of ways to go. And that some of those issues were clearly being raised in the discussion. But one of the issues that's raised, I think in all of the arenas, the three arenas that have been discussing this, is the huge size of chemical space. I personally refer to this also as space-time because the other aspect of it's not just static structures. A structure depends on the timescale you look at it, and reactions are all about converting things and the space that the speed of them, so on. So time is extremely important. Dynamics are just as important as structure. It's made worse by the fact that whilst a lot of the time we've been discussing molecules and maybe taking them into applications, but actually, of course, molecules don't usually exist on their own. As a physical chemist, I did have to go to a huge amount of effort to get my molecules on their own in a gas jet and so on to look at them. And that's really important to understand the nature of the molecule. But most of the time, well, if you're lucky, you have a crystal, and crystallographers have been very good at determining structures and sharing them and setting up a whole economy that ensures that we have the CSD and other things where we can get hold of reliable crystal structures and share them. Though, of course, there are far more structures determined than even there reach the public. And mixtures, we get materials, because in general, things are not just crystals, but they're made out of that. Sometimes you have the semiconductor area where we work with very, very pure crystals. Other times we've got amorphous materials, complex formulations. Most of the things that we put into our bodies, into the car engines, whatever else, are very complex formulations. So there's an engineering aspect here, a level of complexity that builds up from the molecules towards the materials. But of course, in the end, it's the devices and the machines that we're interested typically in trying to get to work. So scales here, whether we're going after the drug targets, personalized medicine, whether we're going to people and animals and the disease side, or whether we're looking at the environment, precision agriculture, the impact on the environment, the relevance of genomics. This is a huge, huge area. And one of the issues that comes up that perhaps we didn't address that much is that when we make some molecules, we might be using in the device. More and more now in the kind of circular economy, we're worrying about recovering those materials. We're concerned about the effect those materials have on the environment, even if we're not directly putting them into the environment. So Wendy has to worry about that directly because she's spraying things in places and they better act there, but better not do more than they're supposed to. But other times we don't even think about it because we make this device and don't worry about where it goes into the environment until it's disposed of, often improperly. So that huge scape of things that we need to consider is something that is often beyond the minds of a single chemist looking at it. And this again is somewhere where the computational side, the access to information, the highlighting information, the linking of information together becomes extremely important. But chemical space is vast, yes. Well, we've done a pretty good job without the computers at doing lots of interesting chemistry. So how did we manage before? Well, frequently we're inspired by nature because we were trying to interfere with nature. So we looked at nature, we see what's going on there. And nature's had millions of years of evolution to play with the chemistry, if you like, try lots of stuff. So by looking at it, we've short-circuited a lot of investigation of a chemical space. Of course, it's only a particular biological chemical space. There may be many other regions. In fact, of course, we do that with a lot of our devices and use other properties. Imagination and creativity of individual chemists, of course, has been extremely important too. So the puzzle perhaps is, yes, we've managed so far, but now we can envisage so much more, but we're really not sure about it because we have some problems with our chemical space. And one of the problems we have is been highlighted that we need to explore lots of molecules, but the space is vast. So we need to make lots of molecules. And if we make lots and lots and lots of molecules, we can afford to make less and less of each one. So I do point out that one thing that's again came up in a few of the talks and the discussions actually in the Netherlands as well as here is characterization techniques are going to be extremely important. So we need to continue to work on that to do nano, picoscale synthesis and characterization in context, in the device, in the cell, or on the field. This type of information is extremely important, but to get it for the range of molecules that we want and the range of materials, we've got to be able to work with very small amounts of material. So this is extremely challenging. Now, one of the interesting things that would make a lot easier to deal with chemical space is if we had a map. And quite a lot of the work that goes on, many of the people talking today have been working on this, is to actually try and create a map of chemical space. Well, when I was looking around this to give some talks actually to some postgraduate geographers, I won't go into why I was giving a talk to postgraduate geographers, but I discovered that there are laws of geography. And Waldo Tobler came up with the first law: everything is related to everything else, but near things are more related than distant things, which is great. And if we had a map and we knew how far things were, we'll be fine. Well, we don't have the map, and actually we're not all that clear on what distance means in our chemical space. So this comes back to some of the fundamental challenges in understanding, even if we have the data. Turns out there's a second law, which is the phenomenon external to the area of interest affects what goes on. I interpret that as surrounding molecules affect the behavior of the molecule you were thinking about, i.e. materials often reflect different macroscopic properties than the microscopic property or the individual isolated molecule. So we've got a lot of work to do here. And perhaps there's a subtlety here that as we do these calculations, we do this they use these models so that we don't have to make as many molecules when we're searching for a drug or an insecticide or some intervention. But to do that, we'll use these models. But to train the models, we need a lot of data. So it would be interesting to know in the end how much we win by. But longer term, at the moment, so in the medium term, certainly it seems we're winning by creating a lot of the right sort of data and training the models on them. I'll come to the models in a moment. So one of the aspects that certainly is flowering in the last 10 years or so of artificial intelligence is the machine learning aspect. We must not forget, and I'll come back to it, that traditional AI, reasoning systems, expert systems are really important too. But machine learning is certainly important. And we've seen a lot of examples have come up in the talks around types of learning. And I'd just like to reflect on when we're in my other capacity in teaching in the university, we are learning and teaching. Does learning mean just coming up with the answer, or does learning mean you know how you got the answer, and even more, why that's the answer? And I think I just pose that in your mind, because whilst we have these sort of classifications of AI, and we're not dealing with the general intelligence that will maybe take over the planet in due course, dealing with our narrow AI, we had down this diagram here of machine learning, and we talked about the different types, unsupervised, supervised, reinforcement, particularly reflect in some of the talks that have been taken over about active learning. Actually, I like that. That's the interaction between planning the experiments, typically with the people and the computers and the experiments. But in the end, some of the time it is good enough to have the answer. What molecule should I make next to get the best drug? What is the next best drug? How can I get a better solar energy material, conversion material? But in the end, as a scientist, I am about understanding why that was the answer. So a lot of this is to perhaps attempt also to extract the answers from the machine. Why did it get there? I understand when AlphaGo was working and kept winning, they had to understand some of the strategies. And it was really interesting because they were strategies that had not come from any human game. No human had ever played this strategy. That was easier perhaps to see the strategy. It's much more difficult when we're looking here into the chemistry data. Now, we've been talking about the need for a lot of data, so we do experiments. You could think about the experiments in quotes. They could be computer experiments. I really like, we've done it as well as Christoph's example, where you can actually generate lots of data to go in. That's much more like the AlphaGo sort of example and play the machines off against themselves. So we get, I like the sort of activation curve here, we get our big data, but the more we have, in a certain sense, the more we throw away. That if we get an understanding, we've got all this data, once we've understood what's going on, to some extent, the chemical information is only useful if it actually takes up less than the data that we were driving with. So we have this sort of intriguing problem of creating a lot and potentially throwing it away. But as highlighted by you all, we do not actually throw it away. The important thing is to make it available to everybody. Now, why is it not going? Oh, there we go. So when we do this and now apply anything from original sort of QSAR predictions to the machine learning, we will take our molecular or perhaps crystal structure. It's represented typically, as been highlighted by a number of you, as a graph coming through. That it gets into our different types of typical neural networks. And then I have to move pictures of you all out of the way. We get some sort of, in here we have a representation of all our data, which is on a much smaller dimensional space than we started with. Now, in the original classical chemistry approaches, we would think what sort of aspects of the properties of these molecules that we know about are actually determining the properties that we would like to know. And that we use to build the latent space, the small space. In the more recent types of machine learning, you train the molecule one way or another to try and find that latent space, that reduced space, which embodies the critical information from which you extract from the data that you know, and then you use that nice, simpler, even though it can be quite complicated model, to be able to predict the new information. Amusingly, I was on a course a few months ago for writing poetry for scientists. And it was really great fun to do. And whilst we were being explained that one of the ways that you made your poem was to write out all the things you wanted to say, if you like the novel, that was the data, then you have the poem is the actual bare minimum explanation, the core of what you're trying to say. And I rather liken the latent space to the poem. So I think we need more poems in chemistry. That will certainly challenge many of our students. But one of the problems that certainly my kids have when trying to understand why on earth you've got a poem is actually understanding what the poem is saying. And you have to think about it really carefully. And getting that information back out of the poem can be quite a challenge. And I think that's mirrored by the challenges of trying to get the information out of these neural networks. And we really need to know if we're going to do that, if we're to learn from those. Sometimes we just need the answer, but a lot of the times we want to know the why. And now, one of the things I highlighted, and I think again it came through, is it's not just the molecules on their own, it's the molecules being used. What do they do? And we understand about making measurements in the field, the sensors, IoT, in the lab, outside. These things are really important at getting us the information we need. But also related here is that we want to go from the single molecule properties to the multiple molecule properties. The complex mixtures. And our techniques typically there rely on using our system mechanics, running molecular dynamic simulations, and those themselves, perhaps less spoken about today, are sped up enormously. I think Christoph may have mentioned this, that these simulations themselves, the force fields are developed now using machine learning. The integrations can be sped up frequently with machine learning. That's being developed, identifying patterns, enhanced sampling, so on, making better use of your computational resources by being clever, or rather getting the machines to be clever. This, I think, is a huge growth area and will enable us to get far more useful information out of what we measure. What's really nice to see, I think, though, is it's not just a question anymore of having some molecules we measure, use that to get a model, take our favorite library that we happen to have got piled away somewhere with 1 million molecules in it and work out which 1,000 we will actually test. That's a great way of filtering out. Or you might think, once you've got a model, I'll think up a new molecule and see if it's any good. This is very useful, but the modern generative models can actually come up with suggestions of molecules to make, and even more so build into that loop actually, can you make them? Well, first of all, can you buy them? If you can buy it, buy it. But are they makeable? At the moment, there's probably not worth suggesting a molecule unless you really, really think it would be fantastic that you don't know at all how to make. And a lot of the work on machine learning driven systems, reasoning systems, knowledge-based systems for predicting synthesis routes have become extremely useful to the chemist. Proteins, Lucy spoke about, as many people have mentioned, AlphaFold and AlphaFold2, and the fact that this data is being distributed. I think this answers one of the ways in which we can see the imperative to share the data when we can. And we ran a series recently about machine learning and proteins and got a cartoonist to put together some pictures for each of the talks. Very rich. Of course, in response to that, DeepMind published its paper in Nature. Nothing, just entirely coincidental in the timing, I'm sure. But one of the nice things about the proteins is, of course, you can, once you've decided your sequence, you can get it made. May cost you a bit. And if you've got something out there, you can run the sequences in the other way. So it's a really rich area to proceed. And it is an example of sharing some of this data. And this brings back to what is probably the key point that has been around everybody's talk and everybody's comment, is about, for data-driven, you've got to have enough data. It's got to be of good quality. Well, it's certainly got to be of known quality. Poor data that you know about the uncertainty and you know what's going on could still be useful. So provenance, the audit trails, these are really important things to have. And it's got to be available. Talking about back amounts of data that sit in boxes, I think Tony was lucky to have it on disk at all. Typically, the data is sitting in a box. It's printed sheets that have got slightly faded. And when we first started the science program in my group, I haste to say it, nearly 20 years ago, we wanted to leave the fixing of the past to Peter Murray Rust. And we thought we'd fix the future. And I'll say some more about that with the electronic lab notebooks. We've come to realize that, well, Peter's done a lot, but he's moved on, given up a bit on chemists. There is a huge amount of data revival that is needed. And I think it's in that way one should look at the data. It's not digitizing it, it's reviving it to make it useful now. And I think a lot of people are discovering that they could and do have extremely useful data hidden away that one needs to work on. UPAC being one of those. Actually, it's going through itself. What are its resources? What does it have? And how can we make those digitally available? Graphs, well, that's come up a few times. Well, maybe there's not much time to say this, but molecular graphs, yes, we look about that. But as Nathan mentioned, knowledge graphs. So graphs are a great way of combining data, whether that's structural data or property data about a molecule or other information you know about chemistry. And bringing those all in to these neural networks can be done using the sort of graph concept. But IUPAC's role in dealing with this has been about the language. So standards are really important. And standards are really difficult, but we've got to get much better and faster at doing them. And we need the standards for the data. I put up the example of plugs. Some of you, if and when one can travel, you may see there are some very clever sockets and plugs that now can work across multiple standards. That's an interoperability issue. And we need to have much more of this worked out in chemistry for machines as well as for humans. But I think it's really important that both humans and machines can understand the data. But not only for the data, but the processes, the models. These models are very complicated. They're built with particular bits of software trained on a data set. We've seen all sorts of issues about trustworthiness of models because they were trained on biased data. So communicating the process and having these processes is really important. Can mention in this in terms of preparing the data to be published in a good form. We worked right at the beginning of RE Science about publication at source. It should be the professional responsibility to prepare your data for some other people to look at it. Frequently, that's you 6 months later, a year later when you're writing your thesis, but that's not, we don't get that into the students. And the problem is, highlighted, a number of you said, it's the tools. If the tools were there, we wouldn't be in the mess of it taking 6 months to prepare the data for publication because it would be much more ready. And that's another area of the ELNs. But the process description is still extremely hard. And if you, but this Edward Denning was responsible for a lot of industrial automation innovation. You know, if you can't describe the process, you probably don't know what you're doing. And I really do believe that when you're vivaring students, if they can't describe it, you really know there's a problem. But we find it very difficult to put that down on paper. Uncertainty, I've mentioned a bit of a talk above, is really important to understand the uncertainty in your data and know whether you need to go do something about that. A lot of this also turns up in the models when you look at where it's the most uncertain points and therefore know where it would be most valuable to go and collect some more data or improve your models. I would like just to reflect for a moment on where we came from with Alchemy. You know, there was a lot of belief that you could turn lead into gold and things like that. Very difficult to do, but not on a computer, much easier to do on a computer. Why is this relevant? Well, a lot of chemical space is discrete. There are molecules, and it's quite difficult to turn one element into another. But in the middle of a quantum or macrodynamic simulation, you can do this. So you can turn the discrete chemical space into a continuous chemical space. You might think that would make it worse because it makes it even bigger, but it makes it more amenable to a lot of standard mathematics. And a lot of traditional mathematics, and that were chemists, if they're brought up at all in it, will deal with that, become more available if you understand about these smooth transitions around between the elements. But another rather interesting area for this is actually with metamaterials. We can actually make a sort of chemistry on a different scale by carefully constructing pseudo elements, if you like. And there we can play lots of games. And that's another whole area in which we may want to do a lot of calculations and a lot of modeling for which we're rather short of data. However, it's all very well to have the wish to have the data and the wish to model it, but if you don't have a decent architecture to collect and maneuver and project your data, you've got a real problem. So the information architecture is just as important. And part of that is the ontologies, the semantic web, the metadata, however you want to describe it, that is needed. And it goes, so FAIR is an objective to have your data findable, accessible, interoperable, and reusable, but we need the technologies to do that. UPAC can deal with some of this. What is really interesting is that my observations is FAIR is a concept much more understood and used in industry than in academia. Partly because industries keep buying each other and discovering they can't actually move the data from one part of the company to another. And they're all about sharing the data to get to an end. Whereas there's been highlighted, there are certain parts of academia where sharing the data may not be so useful to you. And that comes down to trust and the reasoning. And one of the reasons why DeepMind was maybe able to do things that we couldn't is because they were assembled a team who's responsible for getting a result, if you like, rather than individuals trying to prosper in their own career. That sounds a bit negative, but many of the rewards within academia are not necessarily right, and professional responsibilities are not necessarily being described and resourced in a way that UPAC may be able to say something. But even in areas, Wendy mentioned about sharing some of the data between farmers and so on. We've done some work with the food networks, and of course nobody really wants to share too much data, except until there's an emergency, where everybody wants to share the data as quickly as possible to get the emergency out of the way, find out where the contamination in the food source was. And what we need are trust frameworks to enable this type of sharing and information exchanges to understand where the data goes and how it's moved around. As exemplified, blockchain is not necessarily a solution, it could be part of it, but a trust framework is clearly essential, and understanding how to imbue the system with trust. Not simple. And absolutely, UPAC must drive all of this work on these ontologies and the methods of sharing chemistry data. Because if we don't do it now, it will be done first by somebody else. Already the biologists who see the need have encoded more chemistry perhaps than the chemists have, but it's not a good idea because that only gets one aspect of the chemistry. Each domain certainly needs to feed in what we know about these systems to ensure that the best descriptions are there. But equally well, it's not something that comes down always from on high. I think if you're a researcher on a bench and you're writing up something and you need to put the metadata tag on it, and the tag that you want is not there, how do you propose a new one? How do you get that into the system? Those are things that we need to work on. This is often would be called something like the objective of squaring the circle, which is known to be impossible. I prefer the metaphor of creating the Penrose triangle, which, as you can see here, is clearly constructible in this piece of architecture. I'll leave you to work out how on earth that was done. But the origin of one of our biggest problems here is that scientific discoveries about abduction. We actually we see a whole lot of things and we abduct a general truth, which is why we always still go looking for outliers, because it's not induction or deduction is formally, and it could all be wrong, or it could be not quite right, which is of course the way we teach things. And I speculated quite a lot on whether we teach our chemistry students by a series of untruths. We tend to teach our neural networks by a series of truths or assumed truths. Perhaps we should think again. And to kind of finish off here, we do need, however, to deal with the case that the human mind is capable of finding things with small amounts of data. By dealing with prior knowledge and noticing things, it gets sidetracked by always assumed linearity when things are clearly often non-linear. Our deep learning networks are struggling because they need all the data. So this is a real challenge for us all. Equally well, the problem of bias. We can't just say this is a bit of chemistry. It doesn't have the same problems as dealing with people. We for example, train for certain medicines by knowing certain levels of genomics that all happen to be, say, European or American, not African, where there's much greater variety. These are real problems of bias that come in all the way through. So explainable, accountable, and reproducible is all needed. But some of this was foreseen by Robert Heinlein, who said when chemistry becomes a discipline, we'll do all the calculations before we get into the lab. Well, we're getting there, and we can do all of that, but I think it misses the point that actually the lab is key. But it's not, the AI shouldn't be all outside the lab, it should be inside the lab too. And that's where the ELNs are needed. And the big difference I would have with some of the stuff around ELNs that is being done now is it's great for recording the details, but where's the story? Why did you do it? What happened? And we encourage our students to put the story in. The lab was in a mess this morning. Somebody has pinched all my equipment. It's important, it's life. And why? And what are you going to do to stop that happening next time? So telling the story is really important. But that means you've got real human stories in there that you need to get stuff from. So AI-enabled ELNs, that's where we're going. Text mining within the ELN, not of the big data sources out there from the literature, just about what you wrote last week, matching it up. So AI in the lab, embedded AI, really important. The costs are coming down. It's not a question of intelligently telling the lab what to do. We need intelligent automation so the lab knows what to do whilst it's doing it. That can all be built in. Some of it's happening, of course, already. And we've heard about that from Untruths, about so much can be done. So much more can and needs to be done. Well, you know, actually, I think the next slide, is there a limit to this? Should we all get up and just let the computers do it? Well, actually, at least one of the things that one of the articles recently in Nature, a little while ago, showed that some of the problems that we might want to know about are computationally the same as the undecidability problem. So actually, we're sort of okay. Does it really matter? Yes, we can still means that thinking about new ways of doing stuff is really important. But this is all a culture shock for chemistry. Labs now may look a little different, but the way people behave in labs now is hardly really any different in some labs than it was 30 years ago. Life can be made much more efficient and much more pleasant for researchers and for a wider range of people who could bring knowledge into chemistry. So we have a community to engage. We need to engage them in understanding how to share their data, how to collect their data, how important their data is, how important it is that we can trust their data, and showing and working with them what the data scientists can do with their data to help them answer their questions. And we have lots of important things to solve. Typical slide with sustainability. Sustainability, we're going to hugely important across what chemistry can do and what chemistry needs to do to be able to be sustainable. But we're in a liminal period here. We are in a transition. Things are still not all digital. You get this, what I call a digital ditch. As you digitize one thing, there's a huge gap to the next, and it initially takes more work. In the end, it is definitely all worthwhile. But we do have some serious problems coming. I believe chemistry is going to be extremely well positioned to be able to answer them, but maybe not by deflecting the asteroid, but by doing lots of other things that we need to do first to mean maybe things won't be quite so bad on the planet if and when the asteroid comes. Want to thank you all. Thanks everybody who provided the input in this, all the people I've worked with, all of the people who were speaking, who provided the material here for me to be able to raise some of the questions and summarize them. And it would have been nice to meet everybody in person, So actually we can reach lots more people, and this video, I no doubt, will be hugely watched as part of the UPAC site. And we're learning to schmooze over the network. That is the biggest challenge. Thank you very much.
Thank you, Jeremy. So there you go again, influencing my thinking to the point where please send me your slides.
Yeah,
I absolutely agree with data revival. In fact, I'm hoping for revival of my own developing solar panel, but that's not going so well yet. I knew you would translate some of the questions I posed in your session and in your presentation, and thank you for the great responses. So we're closing this. This has been an incredible experience, and I appreciate everybody for coming together today. It's been an enlightening discussion, both on the existing applications of AI that 6 of our panelists have been working on, and what Jeremy's thinking for the future in terms of UPAC, digital UPAC. Based on the pace that things move, clearly if we do this again 5 years from now, it will be a totally different presentation. We'll probably be celebrating a lot of the visions that were brought up here. It does appear that there's a natural role for UPAC, and I can tell from the comments that Chris, Bonnie, and Jeremy have made that you're embracing the opportunity and see your place in that. So I'm motivated and excited. I want to thank you for entrusting me to do this with you, to host this panel. It's been wonderful. I definitely see United Nations of Chemistry is going to be enabled by a lot of the efforts that you have to come. So thank you. Thank you again to the panelists, all the work that you did ahead of this. I know there was an awful lot of communication going on to bring all of this together today. From the outside, it looks like it went seamlessly, I hope. So I appreciate everybody for doing this, and I will open the floor to Chris, Bonnie, and Jeremy, just in case you want to say anything before we close.
I've probably said enough, really, but I think there is a huge role. I'm not sure how many years ago that I wrote to UPAC suggesting that we needed a division of chemical informatics. That led actually to Bonnie's committee getting more work to do. But I think this is really so important. It's so important to set these standards, and so critical to UPAC's activity. And we have real experts. We have people who understand the chemistry and the nomenclature and the terminology, who can work with the computer scientists and others. And only when those computer and data scientists start to understand how difficult chemistry is, they realize we're not asking them to be our personal programmers. We are posing them big challenges in explaining what is a complicated subject.
And I just want to add, kind of reinforce what I said in my opening remarks, that as this WCLM closes, it's not the end of the global discussion. You were quite right, Jeremy and Tony. UPAC will build on what has taken place over the last 24 hours. And I add my thanks to all of you for doing this.
Before I go out, let me just thank you all. It's been a wonderful event. And you guys were spectacular. I think this will be remembered in the future the same way the Dartmouth AI meeting is. Maybe that's a bit ambitious, but I think this is a pivotal moment. So thank you all. I'm done before I fade out again. But again, thanks to everybody. It's been awesome.
Thank you, everybody. Enjoy the rest of your day.
You too.
Thanks, Zach, for keeping it all running today.
Yes.
It's worked really well.
Thanks, Zach. Bye-bye.